Water in a bath, honey on a spoon, air around a moving car, they all flow. But what exactly makes something a fluid? In this video, we'll answer that and then meet the key properties every fluid carries, the ones your exam asks about again and again. Let's begin. Here's the test. Apply a small sideways force, a shear to a solid. It deforms a little, then holds that shape. Now apply the same shear to a fluid. It never settles. It keeps deforming layer over layer for as long as the force acts. So we define it like this. A fluid is a substance that deforms continuously under a shear stress, however small that shear may be. It has no fixed shape and takes the shape of its container. Liquids and gases are both fluids. The difference is that gases are highly compressible and have no free surface, while liquids are nearly incompressible and do. Fluid mechanics studies fluids in three ways: statics, fluids at rest; kinematics, fluids in motion without worrying about the forces; and dynamics, motion with the pressure and other forces included. And one quiet assumption makes all the maths work. Although a fluid is really billions of moving molecules, we treat it as a single continuous material. That is the continuum assumption. It lets us talk about density and velocity at every single point. Our first family of properties is about how heavy a fluid is. Mass density, rho, is mass per unit volume. For water, that is 1000 kilograms per cubic meter. Specific weight is weight per unit volume, which is rho times g. For water, about 9800 newtons per cubic meter. Specific volume is just the reciprocal of density volume per unit mass. And specific gravity is the density of the fluid compared with water. It has no units. Mercury's specific gravity is 13.6, so mercury is over 13 times denser than water. A handy shortcut: the density of any liquid equals its specific gravity times 1000. Now the star of this chapter, viscosity. It is a fluid's resistance to flow, the internal friction between its layers. Honey has high viscosity, so it crawls. Water has low viscosity, so it races. Picture a fluid between two plates. Move the top plate and the layers slide by different amounts, a velocity gradient, du by dy. Newton found that the shear stress is proportional to that gradient. Tau equals mu times du by dy. Mu is the dynamic viscosity, with units Newton second per square meter, also called Pascal second. 1 poise equals 0.1 of that, and water is about 1 centipoise. Divide mu by density and you get kinematic viscosity nu with units meter squared per second. Here is an exam favorite. With rising temperature, a liquid's viscosity falls, but a gas's viscosity rises. They move in opposite directions. Last, for part A, the surface effects. Surface tension makes a liquid's free surface behave like a stretched skin because the surface molecules are pulled inward by cohesion. It is a force per unit length, sigma, in newtons per meter. The excess pressure inside a droplet is 4 sigma by d inside a soap bubble. With two surfaces, it is 8 sigma by d, double the droplet, and inside a jet, 2 sigma by d. Capillarity is the rise or fall of a liquid in a thin tube. Water climbs a glass tube because adhesion beats cohesion while mercury is pushed down. The height is 4 sigma cos theta over rho gd. And notice, the narrower the tube, the higher the rise. Let's recap. A fluid deforms continuously under any shear. Density and specific gravity tell us how heavy it is. Viscosity is its resistance to flow given by Newton's law. Tau equals mu du by dy and surface tension, with capillarity govern its free surface. That is part A. In part B, we'll cover compressibility and bulk modulus, vapor pressure and cavitation, and the thermodynamic properties. If this made fluid mechanics click, subscribe to Learn Civil Easy and join our Telegram channel for MCQ practice papers to test yourself. See you in part B.